Hello, everyone. So this isn't intimidating at all, so I'm sure it'll be fine. It'll be fine. So we're looking at neural networks, and this is a very simple introduction. So if any of the maths gets intimidating, just throw things at me. It's not supposed to. And if you find that you're not stimulated enough, then I'm sorry. OK, so I was staying with my friend last night who lives in Brussels. And she asked that question that everybody dreads. She's a linguist. She said, she didn't say, what do you do? She said, what are you speaking about tomorrow? And I thought, oh, crap. How am I going to explain this? Like, there are these neurons, and they work together, and stuff happens. You put in pictures of cats, and a word cat comes out, or something like that. I don't know. So I thought, I'm going to have to come up with some way to explain this to people, and then I'll understand it myself better. So neural networks feel a bit like magic, and hopefully at the end of this they won't. Hopefully by the end of this you'll think they're just really boring function machines, and then you'll have got it. OK, so does anyone know, I'm going to ask questions, so just you've been warned. Does anyone know what kind of things we're trying to work out with neural networks? One of you must know what kind of thing we're trying to work out with neural networks. You smiled at me, so you must know. Here, in the middle. What are we trying to work out?
Well, you can try, for example, to do a classification system, or a system that automatically, from a set of input, is going to decide a value in decision based on a training that has been done with a lot of real cases before.
Yep.
Try to mimic in a way how our brain is working. We learn from some samples, and when we find a new case...
I'm going to have to stop you there because you're giving my talk. Sorry. It was a very good answer. It was one of the things we're trying to work out is classification. So as you very correctly said, we get a series of inputs into the network, and we're trying to work out, is this from group 1 or group 2? So that's one thing that we're trying to work out. You could feed in pictures of, like when you're saying, I am not a robot, and you're doing a capture, and you have to click all of the pictures with cars in and say, that's a car, that's a car, that's a lamppost, that's a lamppost. So one thing that neural networks do is try and classify information. Should have got a clicker. And the other thing is, so classification, I think, has been very well explained. So one classic example is a data set called the MNIST dataset, which is a data set of handwritten digits. And it's a data set that's used in a lot of neural network competitions, actually. And it's trying to, with a new input, work out which digit someone has written. And we'll have a look at that again later. And another thing we're trying to work out is regression, which is not as friendly a word, I don't think. And regression is where you're trying to work out a continuous output. So it could be the price of a house, for example. So again, with this friend, Beth, if I showed her a simple example of a neural network working, the first place I'd probably go is the TensorGround playground. I don't work for Google, but this is brilliant. But then the problem is, what's this? What's the learning rate? What's activation? What's regularization? What's the problem type? Well, we just did that, so you should know now. What's the output? What is a neuron? What is the hidden layer? And it goes on like that. So hopefully we'll answer these, we'll cover these in this talk. In terms of the structure, because this is a deep dive and it's a long session, I want to break it down a bit and tell you what we're going to be looking at. So in the first part, we're going to look at neurons. And there's going to be a description of a biological neuron that would offend a cognitive scientist, so I'm sorry in advance. And then we're going to look at artificial neurons, and we're going to go over some of the basic types. In the second part, we're actually going to look at learning, so how networks learn. And we're going to go over the basics like cost functions, feed forward, gradient descent, that kind of thing. And the final part, then we'll get on to neural network architectures and a bit more. And in between, I thought it might be nice if you had coffee breaks. So I'll try and time it like that. So we'll try and do 45 minutes, 20-minute break, 45 minutes. We'll try and make it easy on all of us. OK, so let's get started with neurons. what is a neuron? Well, this is where we are. So, I'm sorry, I do have notes for this part because I'm not a neuroscientist. So, well, one thing I can tell you without the notes is neurons are the fundamental unit of the brain, or that's a theory. They receive and process inputs from the world, and they send outputs and commands to muscles. Now, does anybody know how many neurons there are in the human brain? 5, okay. 300,000. Let's go. I know Jim knows the answer, so I'm just going to ignore him. It's not 5. Anyone go higher? A billion. We have a billion. Any higher than, I'm going to, lower than trillions. Any higher than a billion? 60 billion? Bit higher? Oh, well, that is a very common number that goes around on the internet about the number of neurons in the brain, actually. But actually, well, it's disputed, as everything is in science. But interestingly, and slightly worrying if you're male, this doctor, I'm going to pronounce this wrong, so I'm really sorry, Dr. Susanna Herculano-Huzel, melted down 4 adult male brains. They were dead first, I should say. And she melted them into brain soup. So I did actually Google images of brain soup, and I stopped quite quickly. So, and then she counted a sample of them. So obviously you don't want to count up to 86 billion because you'd probably die before you got there, or you would. I'm not going to work that out. But she estimated that it was around 86 billion. And that's interesting in terms of the internet number that goes around, which is 100 billion, because 14 billion neurons is actually the number of neurons in a baboon brain. So that's quite a big discrepancy. We're missing a lot there. So let's take a look at this. Back to my notes. So signal outputs from one neuron can excite or inhibit other neurons. So if a threshold in the neuron, so that top left thing there with the green circle in the middle, if a certain threshold is exceeded, then it fires. If the threshold is exceeded, it fires more frequently. So if it gets really excited, lots and lots of fires. If it's a little bit excited, it might not fire at all, or it might just fire in less frequently. So when it fires, an electric pulse travels down the axon into these axon terminals. And, sorry, I just got a bit distracted by that noise there. And neurotransmitters, so these neurotransmitters travel across this synaptic cleft, that space there, and they go and bind into the receptor molecules, and then they go into the next neuron, and that gets excited or inhibited. So we have these signals going from one neuron to the next, and the more excited a neuron is, the more often it fires. But the really interesting and crucial thing about this, and why I'm talking about it, is the connections between the neurons are adaptive. So these synapses can send more chemicals and they can receive more. So they can change their connections. So we have these neurons, which are apparently the fundamental units of the brain, or are they? We'll get to that. And they work together in a modular brain. So there are some really interesting studies where people who lose one sense, like the sense of sight, can maybe, when I say people, I think these studies are actually done on mice, just to clarify, can relearn that ability in other parts of the brain. And the really important thing to remember is these adaptive connections. So now I'm going to look at Linda now because you're from around here. I think the correct term is quartets, the card game. Is that right? Okay, so just think of this as like that. We're going to collect these cards. So we've got biological neurons. They're not that difficult to understand if you take a really simplistic view. And they're the fundamental units of the brain. But are they? Are they the fundamental units of the brain? It's always important in any kind of scientific discourse to examine where ideas came from and maybe look at the other side. So we're just going to take a little look. So these two men won the Nobel Prize in 1906. I cannot pronounce their surnames. I'm really sorry, but I'm going to try. And just, if you're familiar with correct pronunciation, just wince when I do it. So they hated each other. They completely hated each other. So if I've remembered it correctly, Golgi or Gogli or something. Golgi, thank you. Thank you. Golgi invented a staining technique using silver nitrate to be able, for the first time, to see neurons inside the brain. And Cajal? Ramon, okay.
He has two surnames, Ramon y Cajal.
Ramon y Cajal. So that's my very Yorkshire version. I could go more Yorkshire. Ramon and Cajal, but I'll try not to. Also looked at the technique, and he proposed that the smallest unit to look at was the individual neuron, and Golgi thought otherwise. But Ramon y Cajal's view of the individual neuron won out. I knew it would be good giving this talk at Devoxx because someone would be able to correct me. His view won out that the correct unit to look at was the individual neuron. So what happened since then? So in the meantime, McCulloch and Pitts wrote this paper, A Logical Calculus of Ideas Immanent in Nervous Activity. So the ideas are actually more correctly attributed to McCulloch. But they noticed something really important about neurons, a really important property, which is that they either fire or they don't. They're either on or they're off. So 1 or 0, so binary, so logics. They made a link between neurons and logic. And then Frank Rosenblatt did some early work on perceptrons, which was an early learning procedure using binary threshold neurons, which are also called McCulloch and Pitt neurons. Perceptrons really excited people for a while. There was a lot of research, a lot of funding going around into research and the kind of things people could learn from perceptrons. But we're not going to talk about perceptrons because then, unfortunately, a few years later, Minsky, one of the heroes of AI, and Papert wrote this book called Perceptrons that basically, excuse my language, shat all over perceptrons and just said these are rubbish. Here are, well, not completely rubbish, they're still used a lot, but there are some really serious limitations. And so for a while, things kind of dwindled and it wasn't quite so exciting anymore. And I think, if my history is right, things like distributed AI took off instead of neural networks at that point in time. So then in 1986, a theory that had already been kicking around and was proposed by a few different people at the same time made it into the journal, I think it was the journal Nature, with Jeffrey Hinton, Rummelhart and Williams about backpropagation. And that is really, really important. And we're going to come and we're going to talk about that again. We're going to talk about it a lot, actually. So you've been warned. And that was really exciting because now backpropagation was an idea to efficiently learn in networks. So suddenly we have an algorithm that speeds up learning. And with speeding up learning and then greater computational capacity, suddenly we have an explosion of interest in neural networks. And everyone's really excited about neural networks. But not everybody agrees that this is how we should be looking at things, that we should be modelling the brain that way, that I should be giving this talk talking about artificial neural networks and linking them to biological neurons. So, but it is an idea that has been historically pervasive and is now deeply embedded in the way that we think about neural networks. So that was the neuron doctrine, the idea that the fundamental unit is one neuron. So I've kind of explained why everyone is excited about it, but I want to talk about the two different main branches of research. There's one really interesting branch of research. This is Henry Makram, famous scientist, University of Lausanne, working on the Blue Brain project. And so that is using neural networks, artificial neural networks, to better understand the biological neural networks in the brain. So that's using neural networks to understand the brain. And then the other branch of research is using neural networks to understand better a style of parallel computation. And that's the one we're looking at. We're looking at the one that is divorced from biology. And what we're trying to do is we're trying to train neural networks to learn things that we find so easy we don't even think about them. So computers are really good at some things. So first person to answer this question wins T-shirt. Anyone? No? Yeah, it's a lot. That's the right answer. And then, can anyone, and there's no prizes for this, I'm sorry, but can anyone shout out what kind of animal this is? Yes. I mean, I expected more speed and more volume from the rest of you, but maybe you've never seen one before, I don't know. So that's what we're trying to do. We're trying to learn how we learn. But from now on, just to change in terminology, I'm going to leave biological neurons behind. I'm going to leave them to the experts. I'm going to stop upsetting cognitive scientists. I'm going to get on to computers, which is what we all know and love. So this is where we are. We're now at the artificial stage. So, linear neurons. So we're not really thinking about networks yet. We're still thinking about these neurons, but artificial neurons. So we're thinking about, what's his name? McCulloch and Pitts. We're thinking about them linking a neuron firing to a 1 or a 0. So we're looking at some input coming in and some output going out. So here we are. Here's the map. This felt like a great idea at the time, and now I'm kind of irritated that I've put this slide in everywhere. So I'm sorry about that. OK, so let's just look at a function, a really basic function. So we have some input here. So that in the top left-hand corner, in case my handwriting's a bit rubbish, that is an x. That is representing some input. It could be a single value or it could be a vector. And then we've got a little w on an arrow, and that means we're going to times the x by the w. And then we've got another input, b. And can anyone tell me what that looks like, that equation there? So I think I heard someone say line. Line, yep, it's the equation of a straight line. Yeah. When I ask questions like that, it feels like the answer should be more complicated, doesn't it? But that's all it is. So, yeah, so, for example, let's just get rid of the W and the B because they kind of, I don't know, it's a Monday, you're all taking time off work, no one really wants to look at that. So let's just put some 2's in. So yeah, it's just a straight line. So there we go. Y-intercept is 2. If I'd labelled the axes, you'd see that the gradient was roughly 2. And that B there, that's just the bias, I'm going to call it the bias, is just the y-intercept. I'm just moving the line up and down. So I'm just going to draw it in a slightly different way now, with some circles. And same arrows. And there we go again. Now we've got 2 x's, 2 different inputs, 2 different w's, 2 different weights, 2 things to times them by. And we're going to sum them together in the output, and we've got some neurons. So that's kind of what we're trying to do with a linear neuron. We're trying to mimic a neuron by putting in inputs. So imagine they're coming from other neurons. We're going to do something to them, which is to times them and add them together, and we're going to output them. So maybe there are going to be more inputs. And I'm sorry, now my jokes have kind of run dry. There's nothing funny about this slide. So we've got 3 different inputs there. Just going to start. We're at a Java contract. We're at a Java conference. So we're going to index from 0. We're going to go x0 times w0, x1 times w1, x2 times w2. What are we going to do in the middle? No prizes for guessing. Sorry. We're going to add them together. And we get our straight line. So that kind of question mark there where we're adding them together, if you do read the any kind of documentation, do any courses, you'll see it written in a few different ways. You might see the B as a separate thing, like we had on the earlier slides, or you might just see it slightly differently, but we're doing the same thing. Crucially, those W's represent the synapses, their adaptive connections. So what we really want to know is, what should the W's be? What should the synapses be? What should the gradient of the line be? What should the bias be? Because what we're really trying to do is trying to map some inputs to an output linear function. So what can I do? I'm going to show you a little demo, which is hopefully going to be okay. Right. First of all, I know this is Python, okay? It's just you don't need to understand the code. All you need to know is that I'm just making a little data set. We're in between 0 and 1, 20 different points, and I've got some output here, which is I'm just going to add 2, times it by 3, and add some random noise. And then we're just going to look at the graph. Okay, so there's the data, and there's this line here. So what we really want to do is we want to get that line to go through the data. So if anyone is feeling particularly kind of generous to me, could they guess what they think the bias should be? 2.6. Okay, let's try 2.6. And let's run it again. Okay, yeah, that looks good. Okay, so now let's try changing the gradient. Any guesses? I had a few different numbers there. I had 2 and 5 and 3, so I'm going to average to 3. It's not. It doesn't average. Don't work it out. Okay, yeah, that's good. Okay, excellent. Nice work. Nice work, everyone. So there we go. That's a linear neuron. That's my husband, George. Hi, George. So, right, you answered those questions. Excellent. Thank you very much. So, linear neurons. So we saw them. Great. So, networks of linear neurons give a linear output, which isn't particularly surprising. Sometimes called the identity activation function for that reason. So if anyone has their laptops on them, let's just quickly go to TensorFlow. And I didn't load that up because that would have been really organized. Sorry. And let's just make that activation unit there linear. So these data points here, this is a classification problem. We are trying to work out if a new input, if a new example that we haven't seen before should belong to the blue dots or the orange dots. So don't worry too much about what's happening now. We'll work through all of this throughout this time. But the thing I just want to show you is that if you make the activation unit linear, that we're not going to be able to separate this data. This will run for a long time, so you're going to have to take my word for it or open up your laptops and try. Okay. I'll just leave that running. We'll come back to it. That's what we want. That's what we want to get. So that was a linear neuron. A little bit of maths. I hope it was fine. I'm saying that, but most of you are probably much better at maths than me, so don't feel too patronized. The output is the sum of the inputs times the weights. We have a linear output. Awesome. So now, binary threshold neurons. We talked about McCulloch and Pips. We talked about neurons being on or off, firing or not firing. Here is the map. You know that you're getting closer to coffee, so it's good. I want to go back to this picture of a neuron again. Also, I just like it. I like it as a picture. And here we have our inputs going in. We've got our sum in the middle. So what's missing? We want to activate it. We want that activation of the neuron. We want it to fire. We want something to happen. So, here we go, some more maths. So the binary threshold neuron says, okay, if the sum of all the inputs times the weights, if it's greater than the threshold, I'm going to fire a 1. And if it's less than the threshold, I'm going to fire a 0. So we just fire, it's just 1 or 0. It's one or the other. It's not that exciting, so I didn't do a demo on it. Sorry. But one thing, if you feel like it, and if you feel like doing some programming, try and solve the XOR problem. Does everyone know what the XOR is? Yeah, so it's fine. Try and solve it with binary threshold neurons, just as the problem is without adding any extra dimensions. And I've kind of given the answer there by writing why not, haven't I? So it doesn't work. Don't try it. You'll waste your time. Okay, so that was the binary threshold neuron. Hooray. Logistic neurons. Now this gets more interesting. So again, we have our inputs. We want to do some kind of activation. So what we're going to do is we're going to apply this function. If you're taking notes from this, don't draw that graph. I'll show you a better picture of the graph because it should look like an S and it's not very good. But I will show you a better picture of that. So we're applying this function to the inputs. And what that function basically does and what the graph is going to tell you is that it's squashing the output between 0 and 1. But the output can form on this non-linear line. Non-linear? Non-straight line. So let's have a quick look. And again, let's hope this all works. And I'm just going to show you a better picture of the graph first, because I'm ashamed of my other graph. So that red line there, that is the sigmoid function. If anyone is interested, and if anyone's kind of feeling a bit understimulated right now, the blue line is the derivative, and you can work out the derivative by hand if you feel like. So let's just take a quick look at what the sigmoid neuron can do. Again, this is Python. Don't worry too much about it. I'm sorry, this is a Java conference, and I'm doing this in Python. I will address this in a later part of the talk, when inevitably there'll be a question about programming languages. So I have some input data again. This time it's between -3 and 3. There's no particular significance to that. It's just input data, 100 data points. I'm going to try and map input to the output using the sigmoid function. Okay, so after one iteration, it's not that great. What I'm actually doing is running this through a neural network. After 5 iterations, still not great. 50 iterations, good. Okay, it's learned to map the function. If it was a linear threshold neuron, and you'll have to take if it was a linear neuron, and you'll have to take my word on this, it would not be able to map the inputs to that output. The reason it can do this is because of that S-shaped curve. So what we can do is we can chain different logistic neurons together to get a more complicated output from a functional point of view. So we're mapping a function. Oh, there, it's even better. Cool. Right. So that's logistic neuron, real valued output between 0 and 1. We can map nonlinear functions. Yes. Okay, we're getting closer to pictures of cats. So go back to TensorFlow. Let's see how that TensorFlow thing is doing, actually. Let's just check on that. Okay, yeah, we're still going with the linear neuron, so we'll just kill that. It's probably had enough now. And let's try with sigmoid. It's quite a fun thing to watch if you're bored. Okay, great. So what this picture represents is we have the input features, and the input features are the x-coordinates, so up or down. We have these data points. They lie in different places in this space. Some of them belong to the orange data set, some of them belong to the blue data set. We've asked the network to try and work out if a new data point comes in, where should it be? Should it be in the blue range or the orange range? And we will talk more about this. Okay, so what kind of problems... Oh yeah, no, this is a question for you guys. What kind of problems can the logistic neuron solve? Does anyone know? I'm going to start making eye contact with people and picking on them. So does anyone feel like volunteering as tribute?
Maybe something like the smog level of cities, or something detecting the more higher rates and the lower rates?
Yeah. Yeah.
What was his answer?
Thank you. Maybe detecting smoke rates above a city, whether smog, whether it is higher or lower. Yeah, so we can work out classification problems with the logistic neurons. Which we couldn't really do very well with linear neurons because we're finding a linear function. So we've got a bit more versatility. So that was the logistic neuron. Math's a bit more difficult, especially if you look into the actual function, you try and work out the derivative. It's a bit more difficult. Rectified linear neurons. Now, these are really, really popular at the moment. So all the cool kids are using rectified linear units. So again, we're going to activate our inputs. We're going to go to the output. The output looks like this. So what we're saying is, when you sum up all the inputs, the output is going to be 0 if the input's less than 0. Otherwise, it's going to be this linear output. And what can it do? Okay. Let's take a quick look. So here's what the function looks like in a better version of the graph, because it was drawn by a computer and not by me. And that is the derivative, if anyone is interested. Derivatives will become important later, but you don't actually need to remember them for the purpose of this talk. So now let's look at a really simple network. Again, let's show you it and then I'll talk through it. I've got these blue dots are the output, so I've just made a function. Anyone who reads the small print can see that it's the sine function. And I've asked the neural network to see if it can work out that it is the sine function. So that's what what I've done is I've fed in some data and I've given it the answers, and the answers correspond to the sine function. And the network then has to work that out for itself. So the rectified linear units are very fast and very efficient at working things out. There is another, so I'll just do my summary, before I move on. So you can go to TensorFlow again and try the rectified linear unit as the activation function and compare the speed of sigmoid. Let's actually just do that now, because I think we watched as the sigmoid function took shape. We're keeping everything else exactly the same. Let's try rectified linear neuron. So fast. There's no time even to relax during that demo. Just have to move on to the next thing. So, okay, we have the rectified linear neurons. Slightly easier with maths, I think. Tanh, that's hyperbolic tangent. So that is the last one that we're going to look at before your coffee break. Again, we have our inputs, and the output looks surprisingly like the sigmoid function, and that's because it pretty much is. It's just stretched. And let's take a look at what it can do. No, actually, let's not. Let's just look at the comparison between the two. So, right, blue line is the tanh function, the hyperbolic tangent. The red line is the sigmoid function. And the derivatives look pretty similar as well. So it has a bit more versatility than the sigmoid function, and I'm not going to go into that. But if you're a mathematician, then you'll probably enjoy knowing that it helps to center the data, because it can fall between -1 and 1 rather than 0 and 1. Okay, so let's go back to TensorFlow. Let's take a look and compare that to the sigmoid function. So I'm not going to do sigmoid again. I think we all remember that it was slow. Here we go. Hooray! That was fast. Sad sigmoid. So it's redundant, sorry. So there we go. That's the hyperbolic tangent neuron, output between -1 and 1. And that's that. That's the first section. So we've looked at biological neurons, fundamental units of the brain, working together in a modular brain. We have looked at the neuron doctrine, the idea that to understand the brain, the smallest unit is the neuron. We have linear neurons, our easy friends, so just really simple mapping, identity function. We're not doing any kind of activation, we're just feeding it through. Binary threshold neurons, logistic neurons. Now we can map nonlinear functions. Awesome. We've got the hyperbolic tangent neurons, and we've got the kind of the favorite, everyone's favorite child, rectified linear neurons. And that is, I'll just wait for you to take your photograph, my good friend at the front there. Okay, so we're not any closer to working out what's a picture of a cat versus a picture of a dog. So I guess what we'll have to do is probably have a cup of coffee and come back and try and work that out. So the time is 4 minutes past 2. If we come back for 25 past 2, I'll get started again. Okay, thank you. Just goes to show, doesn't it? You can have all the degrees and you can just not turn something on. So, not that I do, maybe I need a few more and then I'll get it right. So we talked about the individual neurons, and we looked at TensorFlow, and I'm very aware that a lot of the things that on the TensorFlow that we saw, like the learning rate and the output and the input data and the features, we haven't really covered those yet. But now we've got the basics and we've got the neurons, we're going to move on to that. So this is learning in a simple network. We're going to start with some easy examples. We're in part 2. Here we are. We're going to, first of all, look at a simple network. And this one has an input layer, an output layer, and one hidden layer. We're going to call it a hidden layer in the middle. So does anybody know how we would count that? How many layers it has? Someone want to shout out how many layers it has?
1.
1? It feels like it should be 1. It's actually 2. So by convention, we count this as 2 because we don't count the input layer, but we do count the output layer. So the first one, the input layer, is all of the data. And now this word features comes in. Does anyone know what a feature is in this context? So if we have, we're trying to work out the price of a house, what might a feature be? What might contribute to the price of a house?
Location.
Yeah, I don't know how you quantify that, but yeah, maybe you could put in the coordinates of the house. I saw a hand raised.
The size.
Yeah, the size, yes, the classic house price. If you do any kind of basic introduction to machine learning, you'll always come across the house price example, guaranteed, and if you don't, I'd be very surprised. So, and that idea is, I have the size in square feet or square meters of a house, and I want to know the output, I want to know the price, I want to know what the correlation is. And then, again, you might have an input for location. You might have an input for whether or not there's a garage. You might have an input for, again, I don't know how you, proximity to schools, something like that. And each one of these would be a feature. If you were looking at a picture of a cat, what might an input feature be? It's not, the answer isn't the whole picture, by the way. Kale? Tail? Yeah, well, that would be something you're trying to discover. But the input would actually be, it's a mean question, sorry. The input would be a single pixel, maybe, and the red, green, blue value of each pixel. So we need to find a way to put the data in, which is something I'll come to in part 3. And we will find tails. The hidden layer, there are a lot of, if you Google why is the hidden layer called the hidden layer, there are a lot of answers to this. And some of the answers are, well, because we have the training data, all of the different information about a house, for example, and we have the output, which is the price, and we don't tell the hidden layer what to do. And I'm sure I've given that answer before. But then I was watching a talk with Geoffrey Hinton, who has been called the godfather of deep learning. And he's one of the first people to coin the term hidden layer. And his answer was, well, we thought it sounded cool. So we have a hidden layer. We have our output, and that might be the house price. Or it might be a probability. Or it might be a classification described by a probability. So when we move forward through a network, what we do is we feed in for one example, so for one house, all the data we have in the house, we feed in the data to the input layer. And now I drew W's earlier to signify the weights. Here I've just drawn this Greek letter theta, and you can just think of those as W's. It doesn't really matter what symbol we use, so long as we all understand what it represents. And you'll see it written differently in different places, but the important thing is that it is this concept of a weight. Or, if we're remembering our biological neurons, conceptually it's adapting. It's something that signifies an adaptation on the connection, whether we're going to make it bigger by having a large value or smaller with a small value, whether we're going to let more neurotransmitters through or less. So that is our synapse. So now what we're going to do is we're going to times each one of these input values by a weight along the connections. So we might, that x1 in the middle there is going to be times by 2 different weights, and it's going to go in 2 different directions to different hidden units. In the hidden layer, we call those hidden units. So there are 2 hidden units in the hidden layer, and the one at the top is a bias. And that's just to remind you, again, when you think back to the linear neuron, we had that y-intercept. You'll come across biases a lot in neural networks, and that's just to remind you that we might draw it without a bias later, but they're still generally added in. So now we go into the hidden layer, and those colours are to symbolise that some kind of activation is going to take place. So it might be our tanh, it might be the sigmoid, it might be the regularised linear unit, which is difficult to say, or it might be linear, might just be the identity function, might not be activating it at all. And then we're going to times everything by a new set of weights, and we're going to get to our output. And our output is our prediction, or you might see it called the hypothesis. And if we were feeding through information about a house price, features of a house, the output is, what does the network think the house should cost? So that's what we want to know. We want to give it data, and we know the answer. We know how much the house does cost. But we want to know what the network thinks, because we want to train it to be able to get to the right answer. So that is feeding forward through a network. I'm just going to go through that again, because it's a bit dry as a topic. So we're going to move forward. We're going to start with the input data. We're going to times it by some weights. We're going to input it into hidden units, and we're going to move to the output layer to get our hypothesis, which is what the network is predicting. When we looked at the very first neuron example, the linear neuron, and you remember the B feeding in and the X feeding in with the W, and did anyone feel that that was simple? Yeah? We've got some nods at the front there. So the concept is actually simple. So what's actually happening here along the connections is actually quite simple. There's just a lot of it. So it looks like a mess. It looks like a mess because I drew it by hand, but it looks like a mess because there are a lot of connections. So for each individual neuron, what's coming in isn't complicated. It's just that they all connect together in a complicated way. In deep learning, that is neural networks with many hidden layers. So here we just have one hidden layer. In deep learning, you might have hundreds. And then it gets very complex. From the point of view of an individual neuron, it's still just as simple as our first example, maybe with an activation function, but suddenly you have so many of them. That can be very off-putting. So, how many layers does this network have? I heard someone whisper 3. So I'm guessing you're not too confident, but that's the right answer, so great. Now, here's another one, and I've drawn this, I've used a few different symbols. You might have noticed that I've switched them quite a lot, and that's really just to keep you awake, and it's also to be mean, and it's also to introduce you to the idea that if you do read widely, then you'll notice different people using different notation. This is Y hat. It's got a little hat on the Y, and that again is just the hypothesis, or the outputs, the predictions. It's just different ways to represent the same thing, just like we might use the theta, the circle with the line in the middle, or we might use W's for the weights. And some horrible people use beta for the weights. I don't know why they do that. So maybe in this network we might use the sigmoid activation function. So what you'd be doing is you'd have an input layer. And here, to simplify it, I've just drawn the input layer as one circle. I haven't bothered drawing everything that it could represent. And each neuron might get the information in, activate it with a sigmoid function, and pass it along. So you just get something and pass it along. And we could, if everyone was feeling like they wanted some fun, we could get some of you to stand here and we could pass each other things. And maybe, Jim, you could be the output, and we could all feed forward to you. So we could have 2 people standing here, and I don't have anything to pass. That's where this doesn't work, otherwise I would have been mean and made you do it. So, just want to do a little example again. And I've used W's because I was feeling like it when I drew this particular picture, and just to be nice. So, what's going to happen in this? What's going to happen for the input in this neuron? Does anyone know what? Can anyone make a guess? It's one of those questions where it's actually, the answer is surprisingly simple. It's just the question feels like it's going to be difficult. So the answer is that we're just going to add in, oh no, that's not the right answer. Ignore that slide. Let's look at this instead. Just ignore that. Just burn it from your memory. Okay, in this slide, what we're doing is that top left neuron there, I'm going to call that A1. I'm going to index from 1. The next one down is going to be A2. The next one down is going to be A3. The next one's going to be A4. Any guesses for the next one? Yeah, A5. Yeah, I'll stop asking you stupid questions. I'm sorry. So, so what we're going to do to get the input to that neuron is we're going to times the top one by that weight, W21. I've just called it W2 to say that these weights belong to that group. They're the second set of weights. Then we're going to times the second one down by the next weight, the third one down by the next weight. So this is just the first example, right? The first linear neuron. We're just feeding stuff in. And then we're going to activate it with this sigmoid function here. So at each neuron, that's really what's happening. It just, like I said, when you have hundreds of hidden units and hidden layers, it scales up. And it becomes very difficult to see what an individual neuron is doing. So I'm going to show you an example. It's another Python example, but the code isn't important. It could be in Java. Just pretend, because we're at a Java conference, that it's in Java. So again, I've got 100 data points. I've randomly distributed them along a function. So I've said I want 100 data points, and I'm going to put you through, I can't remember if I use sine or cosine here, and then just add a bit of noise, just so they don't fit perfectly on that line. Is that making sense so far? Excellent. I'm aware that as soon as I show graphs like this, everyone kind of goes, oh, God. So let's keep going. So oh, yeah, there we go, cosine functions. The output is a function. I've added some random noise just to not make it too easy. And now, because we just looked at that picture of the network with the 5 hidden units in each hidden layer, I've actually just built a little example. So the network's got these 2 hidden layers. They've each got 5 hidden units. And we're going to use the logistic activation function. And we're just going to see what happens with the network. And if you're feeling a little bit lost right now, what I want you to do is to hold on to the idea that what we're really doing is complex function chaining. We're just, like you might get the number 3 and times it by 5 and pass it to the next function, and that might divide it by 2 and pass it to the next function. We're doing something like that. We're building we're kind of building maths. And I will come to cats later, I promise. So let's run this. Okay, so after one iteration, and you may recognize this example from the last section, the network hasn't done very well. What's happened is we've fed forward through the network once. We randomly initialized the weights. So we've just made them up. We've said just be anything, be something different every time. And we fed the data through that network that we saw. So we went from the input to the next hidden layer, to the next hidden layer, to the output. And after one pass through the network, this is what is predicted. And then we're going to train the network. And I'm going to go on to how to train the network. So I will come to that stage. For now, it's a black box. After 5 iterations, you see it's starting to find its way. It's starting to learn. And again, I will explain how that training works next. Now, after 50 iterations, it's doing pretty well, I think. And after 100, they're great. And if you can see these numbers at the bottom, that's the loss. And I will come to that, but what that loss means is, what's the difference between what the network has predicted and what we know the right answer is? Because we have the answers. We know what the answer should be. We plotted it on the graph. And we fed the input into the network, and we said, see if you can work out what the answer should be. And the loss is, how wrong is the network? So it's getting less wrong. It's quite a negative way of looking at things, actually. But there we go. So that was moving forward through a network. So all we've really done is put in the values to get the output. So if we think back to the linear neuron, we've just put in maybe the 2 for x, 2 for the weight, 2 for the bias, and we've got 6. We've got our answer, but we've moved through lots of layers to get there. So now there's cost functions that I mentioned. So that's the discrepancy between the network output and what the real answer is. And there are different ways to work it out. And again, when you kind of continue on your neural network journey, or if you're already on it, then you'll know, or you'll discover, that there are different cost functions depending on what we're trying to work out. And that comes down to the output layer. So in the example of house prices, can anyone guess what kind of number the output would be? Yeah, what would be the price?
Yeah, the price difference.
That would be what we would work out with the cost function.
Oh, sorry, I thought that was different.
No, don't worry. It was one of those really simple questions again, so you feel like the answer should be a lot more complicated.
So what was the answer?
The answer is, thank you, I always forget to do this for the microphone. The answer is what we'd get out of the net is we're going to get a number out. We're going to get the house price. So we feed in all of the information. What we want it to tell us is the price. Even if it's wildly wrong, that's what we want. We want a continuous number from 0 to infinity. And if we had that kind of output, then we'd have a certain way of measuring the cost. And I'll just show you that now. So for people familiar with maths, then you might notice that this is the mean squared error. So it's the difference. It's also a distance measure between what the answer should be and what the answer that the network has given is. I'm not going to go too much into the maths, but if you're interested, the symbol like that there is sum. So we saw it earlier, it's adding everything up. And then we're taking the square difference and we're getting an average of that. So we're saying for every training example that I put into the network, what's the difference between what the answer should be and what is the answer and the answer that the network gave me? So what's the difference? If we were using the logistic function, that sigmoid function again, then it would be different. And you don't need to understand these cost functions to use neural networks with libraries that are available today. And you don't need to understand this to use the TensorFlow playground. But if you do want to start building your own neural networks, then you do need to do some investigation into different output functions. For the purpose of using TensorFlow and playing on the playground, just ignore this. But this is something that you will need to learn if you want to start building your own network. So, how are we going to actually learn? So we're on to backpropagation. So I just want to start with an example. Each of those blue lines represents a weight. As you can see, we have many different weights in that network. I actually know how many there are, but can anyone tell me? You could say anything. No? Many?
35.
Maybe, yeah, maybe. Let's say 35. Anyone watching the YouTube video can pause and count and send me hate on Twitter. So each of those blue lines is a weight. Each of those blue lines needs to be trained because each of them is a synapse in our brain. And again, here, using brain in the loosest possible term. So what we need to do to train the network is to get the weights right. Because the weights are what is going to... The weights are these adaptive connections. So we need them to adapt with the data coming in to get the output. So for backpropagation, what we're trying to do is we're trying to train these weights. So we're just going to look at the output there, the y hat, the prediction that the network's made. If we change this weight here, the second one down in the first layer, the effect that that is going to have isn't just on that one neuron. It's also going to affect every neuron that it then connects to in the next layer, and it's eventually going to connect the output. So every weight has an impact on the cost of the network, the total error of the network. And so there's an algorithm called gradient descent. And what we do with backpropagation is we start with the very final layer of the network. And this is where it does get very maths heavy, and I haven't included it on these slides. And we work out at every layer how the weights contribute to the cost of the network. Because what we want is for every single weight, we want to know how it affects the output. Because we want to be able to change every single weight. And we want to change it in such a way that the total cost of the network, how wrong it is, decreases. Does that make sense so far? No one shook their head, so I'm going to take it as a unanimous yes. So, having moved forward through the network, and for every training example worked out what the cost is and how wrong it is, now, for every layer moving backwards, we need to work out how the weights are affecting the cost. And if you want to understand how that works, when people ask, do you need maths for machine learning and do you need maths for neural networks? Not if you understand the feeling or the intuition of how it works. But if you do want to work through this, you do need calculus and you do need partial differentiation. But if you understand what I'm talking about and you don't need to go and verify it with pen and paper, then be happy. Backpropagation is a notoriously difficult thing to get your head around. And if you do Andrew Ng's course on Coursera, the machine learning course, not the deep learning AI course, he very kindly says, don't worry, it took me a long time to get backpropagation. It took me a long time to get backpropagation. Every time I feel like I have a grasp on it, and especially in the mathematics, it slips away. So it's one of those things, like you don't need to know every library in Java, as long as you know how to find it. You don't need to know how to work out backpropagation, but you need to understand this concept of moving forward through the network to get the answers and get the cost, and then moving backwards through the network to work out why the cost is wrong. How are the weights contributing to this cost or this error? How can we change each of those weights to reduce the cost? Because what we really want is we want a really small difference between what the network says the answer should be and the real answer. In a perfect world, that would be 0. So, I mentioned gradient descent, and we had this nice picture here, this bowl shape. So imagine one weight and the cost. What we want to do is we want to get to the bottom of this bowl. That's the cost, the C there. We want to get to a place where the cost is smallest for that one particular weight. So that looks easy. When we did our example in part 1, and we were shouting out what the gradient could be and what the bias could be, we were trying to get a point where the line fit the data in the best possible way that it could. And in that example, it was convex. There's going to be a point where it was minimal. There's going to be a point, there's going to be a guess for the gradient and the bias when we had the lowest possible cost function. So in one dimension, that's easy. Just need to find the way to the bottom of the bowl. One of the problems with neural networks and one of the complexities, of which there are many, is what if you have a 3-dimensional landscape? Okay? Fine, that's slightly more difficult. We need to get to the bottom of the right valley. So we need to walk across this hilly landscape and we need to find the perfect valley, the lowest possible valley. And that's where we want to go. That's the minima that we're looking for. But the problem is, in the example we made up, or someone correctly worked out the number 35 weights, now we have 35 dimensions. That's a nightmare. So we need a way of getting to the bottom of that. So backpropagation, maths is very difficult, the concept's very difficult. If you feel a bit lost, I'm really sorry. It wasn't my intention. It's a very difficult subject. But that's about as difficult as it gets in this talk. So, training. Before I get onto gradient descent, I just want to mention training. I've mentioned these before, but I just want to go over them again. I talked about randomly initializing the weights. The reason that we randomly initialize the weights is because we don't know what they should be. So if we set the weights, if we kind of predetermined what they were, we could introduce bias into the network. I don't know if bias is the right word in this context. So we want to randomly initialize the weights because we don't want to accidentally send it in the wrong direction in this hilly landscape. We want to give it a fighting chance. So per example, we went forward through the network. So imagine we've got 50 houses. We've got information for 50 houses. For each one house, we want to feed in the information. We want to work out the difference between what the answer should be and what the network told us. And then we want to move backwards in this backpropagation step. And then we're going to run gradient descent. And that is what I'm going to talk about next. So, gradient descent. Right, I'm going to show you a little example. Is anyone here familiar with linear regression? Cool. Okay, so this will make total sense to you. So here's a little Java FX application. We've got some data. We're going to pretend that it represents the size in square feet of houses and the price. And we're going to look at how changing a value changes the cost. So I've written there how theta1 changes the cost. Just think of that as how the gradient changes the cost. So we've got this line, that orange line there, and it doesn't perfectly fit the data, right? So this red dot up here is the cost for that value of the gradient of the line. So the gradient there is 1, and the cost is pretty high. It's like over 5,000. If we make the gradient smaller, yeah, that's right, sorry, just had a conceptual gap there. If we make the gradient smaller, then the cost is going up, the cost is getting higher, because the line is getting further away from the data. So we're getting a really high cost there. Now, in the gradient descent algorithm, what it does is it looks at how that weight, that theta1 there, is affecting the cost. So we can see that moving the gradient down is making the cost higher. So gradient descent looks at the shape of that line there. And it looks at the direction that the gradient's in, and it says, okay, if you're getting higher, then we need to move in the other direction. So the cost is getting, if we take a gradient descent step now, oh, okay, sorry, that's something that's coming later. Let me reset that. Right, we're back up here. If we take a gradient descent step now, we've got to a much lower point, because we've told it, change the weight, but change it in the direction that you think will make it give a better cost value. So that's what gradient descent is doing. And the reason it's called gradient descent is because we're looking at the gradient in this graph here, the graph of the cost against the weight. And we're saying, if you're getting higher, if the cost is increasing as the weight gets smaller, then you need to increase the size of the weight. You need to go the other way. And gradient descent works like that. Any questions about gradient descent? Because it's not the easiest thing. No? Okay, cool. Let's leave that for now. Right. So I said here that we run gradient descent. I didn't say whether we did it per example for the whole thing. And that's, well, does anyone know actually? Does anyone know when it should be run? Or in the different times when it should be run? Does anyone know? Yeah? Do you know, would you do it, so the answer was training.
What did he say?
Training. So would you do it for one example? Would you do it every time you fed an example through the network? So one house, the data from one house. Would you run a step of gradient descent? Yep, exactly. So the answer is, so your answer is you could do batching. And there are different ways to do it. So online means you run it per example. So again, remember, we're going to take one house, the data from one house, we're going to run it through our network, we're going to get the idea of how much it cost, and then we're going to go back through the network, work out how the weights affected that cost, and then we're going to adjust the weights. And then we're going to take another example, we're going to go again, and then we're going to go back, we're going to adjust the weights, and we're going to take another example. That can be slow. Stochastic gradient descent means pretty much run a massive batch. So imagine we've got a data set, we've got 100 examples of house prices, run all of the house prices through, and then adjust the weights. Mini batch gradient descent means maybe do 10 at a time. So why do we have different ways of doing this? Well, one of the answers is, if you have a data set where you're trying to work out, for example, is something a cat or a dog? And your data set has a nice distribution. So in the first half of the data set, you've got like 25 examples of cats and 25 examples of dogs. Then you can get a good result by running gradient descent after that, because you've got a good representation of what you're trying to work out. But if the first half has got 50 pictures of cats, the second half has 50 pictures of dogs, it doesn't make sense to batch it that way. So it depends on your data how you do it. And don't worry too much about that now. If you're kind of really new to neural networks, just know that there are different ways to do it. There are also alternatives to gradient descent, but I'm not going to go into them. Okay, don't worry. You don't have to do it yourself. There are lots of libraries. Deep Learning for J is a Java machine learning library. Neural network library, which I recommend. So play with that. You don't have to write backpropagation. You don't have to implement gradient descent. It does all of that for you. You just need to learn the library. Equally, TensorFlow if you're feeling adventurous and you like Python. So that was gradient descent. That was quite difficult. Sorry, I lied earlier that backpropagation would be the most difficult thing. So we're reducing the weights in proportion to the gradients. Right, the learning rate. So you noticed maybe the keen-eyed and the awake of you that when I did this the first time, I got something that was, I made a mistake and I said ignore that and I'll start again. Let me show you that mistake again. Let's just change this thing called the learning rate to 2. Let's change it higher. Let's make it 3. And that's where pointing on my screen shows you nothing. Here we go. That's where we are right now. That's our theta value, the weight there, 1.89. Let's take a gradient descent step. Okay, we're getting further and further away. This isn't how it's supposed to be working. Okay, why is that? Does anyone know? Does anyone know what the learning rate represents? Yeah. Oh, sorry, someone beat you to it. The step size, that's right. So when we did this gradient descent and we talked about moving to a point where the weight is the lowest, there's some configuration called the learning rate, which is the step size. The step size is exactly as it sounds. It's how big a step to take at each point. So, where am I? Sorry. Right. What if the learning rate is too high? Anyone tell me?
Might take a wrong decision sooner and go the wrong way.
Yeah, the answer is it might take the wrong decision sooner and go the wrong way. That's exactly right. What if it's too small?
It takes forever.
Yeah, it takes forever. Exactly. Perfect. So here, step size is too big. We've got this neuron trying to get to the bottom of the valley, but it's a giant. So when it steps across the valley, it's going to completely miss it. It's going to go to the other side. And that doesn't matter so much in this picture. But when we have our three-dimensional landscape of hills and valleys, and you're a giant trying to find the lowest point, you're never going to find it. And equally, if you're tiny, and you take tiny steps, it's going to take forever. Okay, so I showed you that. So now I'm going to show you an example again of the learning rate, just to really hammer that learning rate in there. And back in the Python console, apologies, people who hate Python. I was like you once. Okay, I've got a really simple network here. Let me actually just show you that again. Here's my really simple network. This is much friendlier than all of the other examples that we've looked at. We have one hidden unit in one hidden layer. We're just moving from the input data to this hidden unit to the output, the y hat. We've got 100 data points between 0 and 5, and the output is a function. And this is the example that we looked at in the beginning. So it should be, the answer should be something like 3x plus 2. That's what we want the network to work out. And that's what we want it to show us. We're using the linear function because it's a linear problem. So there's no problem, no limitations using that activation function. So after one iteration, we don't have a good example. Sorry, that's not after one iteration. That's with a learning rate that's too high. And so what's happened there is it just hasn't found where it should be, and that's where it should be there with the input data. It's taken a really big step and it's got all of the predictions wrong. Make the learning rate a bit lower, it's still wrong. That's better, okay, so we're getting closer to a good learning rate there. And the predictions are getting close to the input data. And again, maybe that's a bit too small and it should have been run for longer. But the point is that the learning rate is something that you have to configure. You can have like the perfect network. You can have the perfect network for your problem. And if you have the wrong learning rate, then you're not going to get anywhere. And that is a hyperparameter. It's a hyperparameter because it's something that you need to configure in order to tune the network. Let's go back and take a look at TensorFlow, actually. That looks cool, doesn't it? We'll come to that. TensorFlow Playground. So here we go. That's the learning rate. So does anybody feel like they understand the learning rate? Everyone put your hands up. Come on. Yeah, thank you. Yeah. OK, there are some hands down. Do you want me to start again? No? OK, good. Sorry? Scale what? Sorry?
Yeah, these are not random numbers, I guess.
Oh no! So this is the people who developed this at Google helping you out by giving you some starting points. I think it would have been quite cruel of them if they just made it a number input box, especially for beginners. Yeah. Okay, so that was the learning rate. So we have our giants and our very small people. Underfitting. Does anybody know what underfitting is? No? Yes?
You don't have enough features for your problem, so the predictions get wrong because they're not complex enough for the problem.
Yes, so the answer there was you don't have enough features for your predictions, so you don't build a model that's complex enough for your problem. And that's the right answer. So imagine this was meant to be a snail, by the way. Imagine we're trying to classify between the pink dots and the grey dots, and we use the linear activation function. Well, that was stupid, wasn't it? So we didn't get anything. So the network's too simple. So you could try more hidden units, you could try more hidden layers. I've been asked before, and I'm sure everyone in my situation has been asked this, how do I choose how many hidden layers and hidden units to use? And that's one of, I have the most irritating answer for that, which is, well, it depends. So, all the activation function isn't suitable, like you said. We can't map a complex enough function. So maybe we need to try something else. So that was underfitting. Predictions don't fit the data well enough. Overfitting. So apart from anybody who didn't previously know the answer to this question, can they tell me what overfitting is?
Where you use too much training data, not too specific?
Yeah. The answer is when you use too much training data and the answer becomes too specific. Or it might not be that you use too much training data. It might be that maybe you use too many features, or your network is too complicated. It could be for a variety of reasons. So overfitting, you fit the data too well. That looks good. Okay, it doesn't really look like a snail. It's fine. You don't need to tell me. But what if suddenly we get some new examples, and now the network doesn't fit that? The network doesn't predict it. So the problem of overfitting is that the network has learned to fit the training data really well. It's like a... If you ignore this picture, just imagine it's a perfect fit. It's a perfect fit. And now new data comes along and it doesn't generalize. So we'd say it doesn't generalize well to new examples. So one way to do that as a technique is not using all of your training data when you train the network. So we've got 100 houses. We've got information from 100 houses to build our house price prediction model. We don't want to train the network with all those 100 examples. Maybe we want to train it with 60 examples. And then we want to use 20 examples to do things like change alpha, change the learning rate, make it higher and lower, and just test it out on those 20 that we held back and see how that does. Or we want to change the number of hidden units and hidden layers. And we'd use that on the validation set. We'd use the validation set to tune those the network. So the problem, how many hidden layers should I have, how many hidden units in each layer, what should my learning rate should be, that's what you use to work it out. So it's a bit trial and error, really. Well, no, it is trial and error. And then the final bit, when you've chosen your hyperparameters and you've got, right, I'm going to use 0.1 as my learning rate, I'm going to use 5 hidden units in one hidden layer, then you test it on your test set right at the end. And that means that when you train the network, you're not training it on everything, And you're kind of mimicking this idea of a new example coming along. Well, no, you are mimicking the idea of a new example coming along and it not knowing about it and saying, okay, so have you found a general pattern or have you just found a pattern for this data? Because we want that general pattern. There are a few other techniques that, again, I won't go into here, but if anyone is playing with neural networks and they came along to this talk to see if they could learn anything new, then maybe you haven't heard of bagging or early stopping. So take a look at those if you're looking for ways to prevent overfitting. And I will reference the course at the end of this talk that you can take to learn more about that. So your network's too complicated maybe, or maybe you use too many input features. Maybe when we were trying to work out the house price, we fed in information about the location, and maybe that doesn't make a difference to the network. Maybe we fed information about whether or not there's a hose in the garden, and that never makes a difference to the price of a house. Maybe we gave it too many features. So, after overfitting, when we fit the data too well, maybe we need to use something called regularization. So this was on the TensorFlow playground. There was a drop-down for regularization. And that is nearly coffee time, by the way, so don't worry. We need to shrink down the features that we just don't care about. Okay? We need to make them go away. We don't care whether or not there's a hose in the garden. We fed the data through the network anyway, but we need the network to ignore it. So that's kind of what regularization is doing. So maybe the really important thing is the size of the house and the number of bedrooms, and that has the biggest effect on the price. But we've also fed in all of these features that aren't relevant. So we need to make a way to make them quieter. Regularization does this. This slide is a bit misleading because it actually does it by reducing some of the weights, not the input features. But the concept is similar. So it's a way during training to reduce some of the weights, which has an effect of making these features a bit quieter that we're not interested in. There's two different ways you'll see on TensorFlow L1 and L2. If you're interested in what they are, come and talk to me in the break. Okay, so that is regularization. So that's reducing overfitting by making some of those weights quiet. So what have we done? We've done feed forward. We've moved forwards through our network. We've moved backwards through our network because there's no rest for the wicked. And we've looked at the weights and how they affect the error. So now we know how the weights affect the error. We can reduce them a bit or increase them with gradient descent. The learning rate is going to determine how fast we reach this point with gradient descent. Underfitting is when you haven't done well enough. Overfitting is when you've done too well. And regularization is another one of those things you'll see on the TensorFlow playground drop down, a way to kind of reduce overfitting. So please go and get some coffee, have a break, walk around, and we'll come back at past, if that's okay with everyone. Thank you. Okay, so we had the fun section, which was part one with the smiling neurons. And we had the kind of like, oh no, section last with the forward and back propagation. And now this is kind of a bit more relaxing. There's no maths, I promise. I'm not going to try and explain anything. So it's a break for me as well. Instead, we're going to look at networks. So what are neural networks? We had the neurons, we had them learning, and now we're going to have them learning in a network. All of the examples we saw so far, you may have noticed, were a bit basic. So here we are, just your map, just in case we're lost. Data. Right. Before we go anywhere near a network, we need to make sure that the data is in a good place. And I know this isn't a data mining talk. This isn't about cleaning data. I'm not going to explain principal component analysis. I'm going to say the word so I sound clever. But we're going to talk about getting it in the right shape, because I get a lot of questions. I'm trying to do this with neural networks. What should I do? The first thing is, someone asked about features. How do you know what the right features are? What's the data? How do you make your data numeric? This is like 50% of the difficulty of neural networks. Once you've got beyond the maths, okay, then it's 50% data, and it's 50% those hyperparameters, the learning rate, the regularization, the number of hidden units, the number of hidden layers. It's data. Data is the big thing. So We need to map the input to the output, but we need to make sure that the input is in the right format first. So, first of all, has anyone heard of feature selection? Yeah? Cool, great. We've got 3 people. There may have been more. So we need to make sure that when we're picking the house, we're looking at a house price problem, and we've got our data about our house, we don't put information in about whether or not there's a garden hose. No one cares. No one cares, unless you're like a really, really dedicated gardener who just can't walk inside and fill up the hose. Oh, I don't know anything about gardening, you can tell. So we need to make sure that we don't put in data that's not relevant to the network. So this isn't the same as regularization. This is before we even put anything in the network. So there are 2 techniques called, there's feature selection using filters, and there's feature selection using wrappers. Filters look at every feature in isolation. Can anyone guess why that might be a problem, if it's a problem? I've given you a clue, but why do you think it might be a problem? Anyone? Yeah?
Well, maybe a feature by itself is not interesting, but a feature together with another feature may be an interesting fact.
Yes. So the answer was maybe a feature by itself isn't interesting, but when it's paired with another feature, then it becomes relevant. So you might have, imagine in your house price example, you don't have the size in square feet. Imagine you have the length of the house and the width of a house. By itself, it doesn't really tell you anything if you know that your house is 10 meters long. But when you know that it's 10 meters long and 10 meters wide, then you have some useful information that you can use about the price of the house. Wrappers are interesting. We'll go back to filters. So filters look at features in isolation. And if anyone here has done statistics, then I'm going to throw out the term information gain, and then maybe, no, anyone? Okay. So what we do is we look at the feature, for example, and we say, by yourself, how much do you tell me about the output of this data set? And it's fast, and that's why it's good, but it doesn't tell us about the interplay of features, which is why it's bad. Now, wrappers, you can guess where this is going. Wrappers do, but they're slow. And wrappers do because what they do is they look at subsets of features, but they evaluate how effective they are by running them through whatever you're using to try and work things out. So it might be running them through a neural network and looking at the accuracy. It might be running them through a classifier, for example. So I'm just going to give you a little example of how you can do that. So there's a program here. And now I hope you're all going to forgive me for using Python earlier because Weka is written in Java. So I feel like I'm off the hook slightly. There's this, I'm fairly sure it's open source project called Weka. You can load in data. So here what I've done is I've gone, choose a file. These are all Weka files. They're a bit, just think of it as like a CSV. It's not, but load in our data set. We can take a look. Okay, so this is wine. We're going to classify wine. I'm sorry it's not beer because that would be more kind of relevant to Devoxx. And we have all of these features, and I can't even pronounce most of them, but hue, it's hue of the wine. And it's probably a good guess that of all of those 13 features, only a few of them will really make an impact to the class of the wine. So if we go and we look at a filter, so I'm using this information gain filter, and we run it through, that was really fast. We can see that flavonoids, does anyone know what flavonoids are? It's kind of murmurings, I didn't catch anything, so I'm going to guess. Yeah, something to do with flavour sounds good. And proline, any chemists? No? Well, anyway, it looks like they make a difference to classifying wine into different types. If we run it through the wrapper, then it takes a lot longer. So I actually started this running in the break, and it's still running. But that would give us a similar measure of how good each feature is for what we're trying to work out. So that is filters and wrappers. I shouldn't have told you the answer. I shot myself in the foot there. Okay, so can anyone shout out why we'd want to standardize or normalize data? Yeah, or it might be, for example, if you have different features and they all have really different values. So you might have your size of square feet in meters squared, and then you might have the number of bedrooms. So then you've got this input that might be in the hundreds and an input that might be in the below tens. So you want everything to be roughly the same shape because it really helps the performance of your network. And this is the last point before I stop talking about data, so don't worry, dimensionality reduction. So this is the idea that you might have two features that are really highly correlated, and so there's a way to kind of combine them into one feature. So it's like the timesing the length of the house by the width of the house. And I apologize to anyone who does understand principal component analysis, because you're probably going, that's not really what happens. It's all eigenvectors and magic. But so let's take a look at the iris dataset. Does anyone know the iris dataset, apart from Jim Weaver? I know you know it. I saw a few hands. The iris dataset is a classic dataset. If you want to start doing some machine learning, you want to start playing with these networks, get the iris dataset, because people have used it so much. If you're trying to work out how many hidden units, you're not sure what the answers should be, you're not sure if you're going in the right direction, it's used as a toy example for so many machine learning problems that you're guaranteed to learn the best way to configure the network. And it's a good way to learn when someone else has already given you the answers, I think. Kind of doesn't really work when it comes to exams, but the rest of the time it's great. So we've got 4 input features. We've got the petal length, we've got the petal width, we've got the sepal length, and we've got the sepal width. Don't ask me what sepal is. And we want to be able to work out between 3 different types of this flower. And so we can use something called principal component analysis to reduce the number of dimensions to a smaller number. And then it's faster to run through our classifier. Sometimes it's more accurate. Has anyone heard of the curse of dimensionality? So that's the idea that when you're looking at a house price, for example, and you have your bedrooms, your size in square feet, whether or not there's a hose, whether there's a school nearby, whether there's a garage, there's a certain point where adding more features actually makes the performance worse. And that's why it's important to do pre-processing like this. So we've got a little example in Python again of the iris dataset. This is what it looks like. And I can't illustrate to you what it looks like in 4 dimensions, so I've done principal component analysis to reduce it down to 3 just to show you what it looks like. So they're the different classes. They're kind of separated in space, not from this angle, but hopefully we'll... There. You see there's a separation. And that is principal component analysis, reducing the number of dimensions down. Okay, so does anyone know who this man is? Shame on you. Shame on all of you. This is Marvin Minsky. This is one of the fathers of AI. This is a wonderful man. And I'm going to show you a little video because I promised that this part of the talk would be nicer. And everyone loves videos. It's like when you're in school and your teacher decides to play like a history drama instead of watching it. So we're going to watch Marvin Minsky talk about some of the problems with perceptrons. Do you remember I told you about perceptrons and his book in 1969 that shat all over perceptrons? Well, this is interesting. This is some of the limitations of perceptrons, but this is some of the limitations of neural networks in general, and it's specifically to do with getting your data wrong or finding that you've actually trained the network to learn the wrong thing. Oh, good.
It's in the picture.
Sorry, I'm going to start again.
Something that they couldn't learn was to count the number of objects in a picture. It's just turned out that that was because of rather obscure mathematical features of the concept of counting, that a reinforcement neural network of the type that many people were interested in just couldn't do that. In order to make a machine that can count.
Okay, so one story that he also tells, but I won't play all the videos, is about neural networks that they trained on tanks. So they trained them on American tanks and Soviet tanks. And they wanted a network to learn the difference between American tanks and Soviet tanks. Useful thing to know. And after they trained the network and they fed in new examples, they realized that it was getting everything wrong. It done really well in training, so it probably overfit it. And it wasn't correctly classifying them. And somebody realized that all of the pictures of Soviet tanks were taken on a cloudy day. So what do you think the network learned? Tell the difference between a cloudy day and a non-cloudy day. Exactly. So data is important, tuning it is important, because the network is only as good as you have taught it to be. So the funny thing about learning with neural networks is that you're learning as much as the network is learning. You're learning how to tune it. So architectures. All of the examples we saw were feed-forward neural network. And Marvin Minsky mentioned looping back, feeding back into things. There are so many neural network architectures that I'm not going to go into them. And I actually don't know all of them. So this is just a subset. But generally, feed-forward are the ones that we've seen, everything moving in fully connected layers through the network. All of the neurons were connected to all of the other neurons. Recurrent neural networks are able to feed back on themselves. I'll talk about them. But you may have heard, and you probably definitely will have heard, especially with image recognition, everyone talking about convolutional neural networks. So I just want to tell you something about them. So convolutional neural networks are a specialized kind of feed-forward network. So you might input an image. So this is just a tiny image, 32 pixels by 32 pixels. It's got 3 different color values. So that's our input. And then it goes into a convolutional layer. And what this does, say you've got your image. It's a cat, obviously. We get something called a filter, and that moves across the image like that and takes data from it. Then we get another filter. It moves across the image, and we get filter after filter after filter after filter. And what they're doing is they're learning different parts of the picture. They're learning little features. So when you have a picture of a cat, and I think we mentioned earlier, it has a tail. A cat has a tail. Most cats have tails. So you can think of it as learning these features. It's learning what makes a cat. Whiskers make a cat. Eyes make a cat. A tail makes a cat. Famously, there have been some problems with Google's image recognition not being able to distinguish between certain types of dogs and mops. So convolutional neural networks have these special filters, and then they might go through a normal layer, like we saw earlier with the rectified linear units, and then a pool layer, which is like a way of shrinking all of the data. It's a bit like the same concept as principal component analysis, and then outputting it in the final layer. So here's like a little idea. We're trying to work out what makes a picture of a bird. And the network has learned that one feature is a beak, and one feature is the body and the wing, and the other feature is the eye. We haven't told it what those features are. We just fed it in. We've used features in a different sense. We've used features to mean the data that we're feeding in. And now we're using features to mean what does the network think is important about the data that we fed in. So when it sees all of those components, it knows that it's made a bird. Imagine we have a jug with a spout that looks suspiciously like a beak. So we have the spout matches up, but it doesn't match the body, it doesn't match the eye, so it's not a bird, as you can probably see. And one thing, if you do, like me, feel like reading the 1986 paper by Hinton, Rummelhart, and Williams, find it's just this wonderful way of describing what's happening inside neural networks, internal representations. The network is learning about the data. We're learning how to tune the network. The network's learning the structure of the data. Some really interesting neural networks that aren't supervised. Everything we've mentioned so far is supervised learning. And that's because we know what the answer should be. We're giving the network the data and we're saying, try and get it to this point, please. With unsupervised learning, we're saying, here's some data, can you find something meaningful in it? And there are some really interesting neural networks, if you look up Hopfield nets and Boltzmann machines, that take this idea and they try and find structure in data. And the way they learn has been compared in psychology to dreaming. They take the data in and they try and reach a point in the data, reach a good point. And then they have to do some unlearning. And the theory is that when you're walking around during the day, you're going bag, chair, Linda, that kind of thing. And you go to sleep, you don't need to remember everything that happened. You need to do a bit of unlearning. Anyway, that's just a side note that sounds interesting and may not make a lot of sense. But these internal representations are what neural networks are doing, which is one of the reasons I find them so fascinating. So recurrent neural networks, we're nearly at the end, by the way. So these deal with sequential data, or time sequence data. So as well as getting all of the information in at one point at the beginning, you're also looking at what you've had previously and you're feeding it back in and looping around. And there are some really really interesting projects with the Google Magenta team, which Jim Weaver pointed me in the direction of, where they're using recurrent neural networks to compose music. So using something called reinforcement learning as well, which is subject of another talk, they teach a network to try and learn what the best music, what the best notes to play next are. And no, I don't have that, but I do want to show you, before we leave architecture behind, an example of a convolutional neural network. So remember I talked about these layers. So this is a project someone's done, and I'll make the link available later. Using that data set I mentioned right at the very beginning, if anyone remembers, the MNIST data set, so all of those handwritten digits. And now I can draw a new digit, and it won't know. This is a new example. It's never been drawn before, philosophically. And it's going to use convolutional neural networks, first of all, using the filters to work out these features, and then compressing it all down to work out that I've drawn a 2. So I really recommend playing with this and having a go, because it's a really good way to visualize what's happening inside a network. So, right, let's go back to TensorFlow. Do we feel like we know what's happening here now? Do you feel like you have a better idea of what's going on? Cool, I'm taking the 3 yeses and the nod as unanimous consent that this talk is a success. So if you could all just feed that back, please. Awesome. Right now we're going to spend a bit of time on the and beyond. First of all, learning paths. Okay, so I actually started, someone asked me earlier, I was a developer who was very, very bored with my job. And then I got a job at Voxxed, which was awesome, with Stefan Janssen and Mark Hazel. And I was doing some learning in my spare time, and I was using Coursera, which is a really cool online learning. You all heard of MOOCs, massive online something learning. I'm sure there's another O there. Stanford University published Andrew Ng's course, General Machine Learning. Start with that. It does include maths. He uses thetas instead of W's for the weights. If you then take the Geoffrey Hinton course, you'll find that he uses W's. It's very confusing. It's really good. It's a really good way to get started. It's free, as is the Geoffrey Hinton course. There's also a new series of courses on Coursera called Deep Learning AI by Andrew Ng. I should say I'm not paid to say any of this, so do check those out. You can take them at your own pace. And then what I ended up doing next was lots of wider reading, and I've gone back to university. So that's the disclaimer. Right, resources. I noticed that someone tweeted something in the break about a YouTube channel, which is really good. So I thought, let's start our own hashtag. Let's hijack one of Devoxx's hashtags. So if you all have come across resources in your own time that you find useful, please tweet them with this hashtag. I'll do the same after the course, and maybe we can take over the Devoxx wall. Who knows? Right, I'm going to go through a series of questions that I think need covering, and then I'll open up the floor. First of all, do I need maths? So you might have your own opinions about this now. So you definitely don't need maths to understand what's happening in machine learning. But if you want to take one of the courses and you want to start looking at your own algorithms, then it is very useful. So don't get put off by the slide, by the way. This is just if anyone does want to go off and do some cramming like I've done and get some textbooks, here are a few places to start. So there's the equation of a straight line. It's a nice one. Quadratics, because you might have something called polynomial regression, where you're not fitting a straight line to the data, you're fitting a curve. Differentiation, that's if we want to get close to gradient descent. Partial differentiation, I'm going to get quieter and quieter and fade out at this before all of the hate kind of reaches peak levels. So, oh look, there's some more maths. There you go. Just the top right one, just don't look too close. It's really useful to understand what's happening. And I used to say, no, you don't need maths to understand neural networks. But actually, if you want to start looking at things yourself, you want to start reading research papers, it's really good to start getting familiarization with this. Did I see a thank you in the audience there? Are you a mathematician? All right. I thought you were a grateful mathematician. Right, what programming language? Okay, so yeah, I use Python. I'm sorry. I've apologized a lot for that. Java. Also, deep learning for J. There are lots of Java options. You don't need any programming language to do neural networks. There are so many resources available. But I do think that Python is really good to quickly write things up. All of my examples that I showed you took a very short amount of time, you could probably tell. But something like, when it actually comes down to performance in some libraries, Deep Learning for J library and the Python library that I ran some of the examples on actually use, I think they use C underneath it all. So the performance is pretty much the same. You just have the overhead of the language depending on the length of the problem. So if it's a tiny problem, you've got more overhead running Java because you have to load the JVM. It's worth learning Python if you're going to do any kind of scientific programming there, or Matlab or something like that. Okay, what should the data look like? So I think we covered that. Any more questions on that? Awesome. Okay, right. This is my favorite question. I'm trying to solve a timetabling problem. Where do I start with neural networks? I don't know. Everything is so domain specific. If you have a problem you're trying to solve with neural networks, you might not need neural networks. You could use something else. If you want to start playing with neural networks, don't look for a problem and then look for a neural network. Look at example datasets. Look at Kaggle.com. Look at datasets that already exist and start playing with them and get a feel for neural networks, rather than think, wow, I have this real-world example, maybe I can solve it. Because you need to learn a lot more about your data before you get to that stage, and neural networks. When do I use architecture X? Totally depends on the problem you're trying to solve again. And the best thing to do is probably to read through the Wikipedia page about different architectures. And the person who gives the best answer to this question wins this T-shirt. Okay, where's the camera? Never. And that's my talk, everyone. So thank you very much.
Won the T-shirt for that answer?
Yeah, he was the only one. Does anyone have any questions?
You showed earlier how with the images in the middle came up from specific features you was detected from the tool you had handwritten. How does it come from these neurons with these weights, from those numbers into those images?
Okay, so the question is, how do you go from numbers in images to the weights in the neurons in convolutional neural networks?
How do you come from basically your neurons with your weights on them to actually represent, how do you represent them as images? How do you come to the fact that it looks like a 2 in that demo?
Okay, so how do you go from numbers to the fact that something looks like... So in the demo I did with the handwritten digits, how do you go from the numbers to looking like something's a 2? Well, so one answer is I'll point you to some resources, and the other answer is a computer doesn't see a 2 in the way that we see a 2. And we're not training the network to see a 2 in the way that we see a 2. So when you actually put an image into a network, you're actually just flattening the image out and you're feeding it in this really long vector of numbers, of different numbers. And the computer isn't learning to see... We understand it as that it's learning to see the letter 2 or the tail of a cat. But it's actually learning its own patterns, the mathematical patterns behind that image of the 2. So it's not really learning, going from the numbers to learning in the way that we'd think it would be. Whereas the other answer to that, though, if you look more into convolutional neural networks, is that convolutional neural networks are based on, I think it's the visual cortex. So when you, reaching back into my mind for a cognitive science class I was in a few weeks ago now, so this might come out really wrong. But when you, in your image field, different points of light are mapped to different parts of your brain. Don't ask me any detailed questions about that because I can't tell you. I haven't done the reading yet, I'm behind. But so convolutional neural networks work in a really similar way, but you wouldn't describe, but we would put the numbers together in a matrix that shows us that they're in a certain place, whereas the computer doesn't understand the same structure.
My question is more about visualization. How do you visualize the hidden layers? So you showed with the two that you visualize the hidden layers. How do you visualize? How do you go from that data in that hidden layers to somewhere you visualize that in that demo?
Okay, how do you go from the data in the hidden layers to how you visualize it in the demo? Someone actually did that. Someone actually made a really cool YouTube video, which I haven't asked permission to show, so I won't show it in this talk. Maybe I'll show it when they stop filming. Where somebody has taken the output of the units, not the weights, but the output, the actual nodes, the units, and they've assigned a color value according to how big the number is. And they've built this really cool visualization of a whole network working, and the data moving through it using these color values, so it shows it firing. So maybe maybe when we finish, I'll show the video. Okay, so I'll show it. Yes.
Can I give a late answer to your question?
Oh, yeah.
It was a bit fast, to be honest.
Oh, I'm sorry. Did I not give you a chance?
No, I was still thinking. No, I think it will all end for us when we stop feeding them pictures of cats and other cute animals.
Okay, so the idea is that the overlords will come for us when we stop feeding networks pictures of cats and other cute animals.
Yeah, I mean, it's, like, it's sort of like we're drugging them, like we're keeping them peaceful, and then if one day we stop that, it's like, well, why not demolish them all?
For the benefit of everyone at the back, this gentleman is saying that we're effectively drugging neural networks by feeding them these images, keeping them... Yeah, I think that's quite... Yeah, I mean, you can't build a flawless system when you're flawed yourself, can you? So maybe if we all stop on the cat subreddits, we'll have more time to devote to neural networks. Yeah, that's a good answer. If you want to counter that, then you can have a fight for the T-shirt. Any more questions? Shall I move on to the video? Yeah. Okay. All right. Let's end the talk. Thank you very much. Shouldn't turn myself off when I want to be heard. There you go.